Welcome to the deep dive. Today, we're tackling something huge. I mean, literally all around us. Our aging infrastructure.
Yeah, it's a massive challenge.
Bridges, buildings, you name it. They're constantly needing stronger, more durable materials, especially in civil engineering.
Definitely.
So today, we're doing a deep dive into some really cutting-edge stuff, an experimental investigation into these new hybrid wraps.
Right. Made from glass fiber reinforced polymer GFRP and stainless steel wire mesh, or SSWM.
Exactly.
And our goal here really is to cut through the technical jargon. We want to pull out the key nuggets from this research for you.
Make it make sense.
Yeah. Help you understand the mechanics, sure, but also the why. Why these findings matter for strengthening concrete structures down the line.
Absolutely. And for you listening, that's the idea. Get you straight to the forefront, uncover those aha moments, rethink what's possible in structural reinforcement. Okay, let's get started.
Let's do it.
So first up, the big picture. Fiber reinforced polymers, FRPs, they're not new, right? They're kind of a staple already.
Oh, yeah. Widely used in civil engineering, especially for strengthening existing concrete structures.
Which is super important with all the aging infrastructure we mentioned.
Yeah.
And environmental wear and tear.
Exactly. Think highway overpasses, older buildings getting retrofitted. You see this stuff applied quite a bit.
And GFRP is just one type.
Right. It's part of a family.
Yeah.
You've got aramid, basalt, carbon, CFRP, and then glass FRP, the GCOP.
Okay.
And GFRP is interesting because, well, two main reasons. It has a high strain capacity. It can stretch quite a bit before it breaks.
Right.
And it's really cost effective. I mean, compared to carbon FRP, it can be 10, even 30 times less expensive.
Wow, 10 to 30 times. That's a huge difference.
It really is. Makes it much more practical for large-scale jobs.
Okay, sounds great then. High strength, low cost.
Right.
But there has to be a catch, right? What's the downside with these conventional FRPs?
That is the critical point. The main limitation, the Achilles heel, if you like, is premature debonding.
Debonding, so it peels off the concrete.
Basically, yes.
Yeah.
Before the material can even reach its full potential strength. Imagine a super strong bandage that just doesn't stick properly.
Ah, okay. So you're not getting the full benefit.
Not at all. And another big one is vulnerability to high temperatures. Think about a fire scenario. Many FRPs don't perform well under heat.
Right. And if that reinforcement peels off or weakens in a fire, well, you can imagine the consequences, potential structural failure.
Precisely, which is why researchers are looking beyond just the standard FRPs. They're exploring these hybrid strategies.
Mixing and matching?
Kind of, combining different FRPs, or like in this study, combining FRP with other materials.
And that brings us to this specific hybrid, GFRP plus the stainless steel wire mesh, SSWM. Now, the SSWM part caught my eye. What's special about the wire mesh? I saw something about the cost.
Yes. The SSWM brings a lot to the table. It actually bonds pretty well with concrete, which is great, and it behaves much better at higher temperatures.
Better than the GFRP.
Yes. And then there's the economics. It's significantly cheaper. Roughly INR 650 per square meter. Compare that to GFRP at around INR 1250.
So doing the math quickly, that's almost half the price, like 50% less.
Exactly. Almost half, which, again, for large infrastructure budgets is a really big deal.
So it's not just about adding strength. It's smarter, more resilient maybe, and definitely more affordable.
That's the synergy they're aiming for. You get the high strength and corrosion resistance from the GFRP.
Okay. But
you add the ductility, the ability to deform without breaking the cost effectiveness, and the better temperature performance from the SSWM.
So a best of both worlds kind of situation.
That's the idea. An effective alternative for retrofitting that tackles those weaknesses of traditional FRPs. It's about practical, real-world engineering solutions.
Okay, makes sense. So how did they actually test this hybrid concept? What did the experiments look like?
Well, the main goal was pretty clear. Investigate the mechanical behavior. How strong are GFRP, SSWM, and these hybrid wraps? And how well do they bond?
Right.
So they used coupon specimens for tensile tests, basically pulling them until they broke. 42 of those.
Okay.
And then 48 dumbbell-shaped specimens to test the bond strength with concrete.
And they changed things up within those tests, right? What were the key variables?
Two main things. First, the number of reinforcement layers. They looked at 2 layers versus 3 layers.
Okay, layers matter.
Definitely. And second, the type of epoxy glue holding it all together. They compared 2 kinds, Cicator 330 and Cicator 30 LP.
Ah, the adhesive. That's always critical.
Absolutely. These variables let them pinpoint what really affects performance.
Now, it sounds pretty straightforward, make the samples, test them, but I read they actually ran into a problem making the samples.
They did, yeah. Initially, they used a tension assembly frame, kind of standard practice, but it wasn't working well.
What went wrong?
They reported inadequate interfacial bonding. Basically, the layers weren't sticking together properly. You can even see gaps. Not good for testing.
So what's the fix? This sounds like a real aha moment in the lab.
It really was. They had to pivot. They developed this customized hand layup assembly.
Hand layup sounds meticulous.
It involved using a PVC mold and applying uniform mechanical pressure just to make sure everything bonded correctly. It shows that getting the prep right is crucial.
Absolutely. Garbage in, garbage out, right?
Exactly. And to add credibility, they used a standard concrete grade M25 for the bond tests, and the tensile tests followed the ASTM D3039 standard.
Industry standard stuff.
Yep, adds weight to the results.
Right, so after all that careful prep, what did the tests actually show? Let's talk tensile performance first. Strength, stiffness.
Right. So no huge surprise here. The highest ultimate load and stiffness came from the pure GFRP samples. GGG, that's 3 layers of GFRP, and GG, 2 layers.
Makes sense. GFRP is the strong stuff.
Precisely. And conversely, the lowest strength and stiffness were in the pure stainless steel wire mesh samples, SS and SSS. SSWM isn't primarily about tensile strength.
But where does it get interesting? The hybrids, I assume.
That's where the balance comes in. Configurations like GSG, that's GFRP, steel, GFRP, and GS, they showed really promising performance.
How so?
Well, take GSG with the Sikador 30 LP adhesive. It reached nearly 90%. About 89.46% actually of the load capacity of the pure GGG sample.
Wow, nearly the same strength.
But using fewer layers of that expensive GFRP, that's the efficiency gain.
That's huge for cost. And what about ductility? You mentioned SSWM brings ductility. How did that play out?
That's the other side of the coin.
Yeah.
Ductility is, how much it stretches or bends before it snaps.
Right. You don't always want brittle.
Exactly. The pure GFRP samples, GG and GGG, they were strong, but they failed abruptly. Brittle failure. Lower rupture strain.
Okay.
The SSWM only samples, much more ductile. They absorbed a lot more energy before failing.
And the hybrid.
That's the sweet spot. The hybrids GS, SGS, GSG showed significantly better deformability.
Give me an example.
Okay. The GS configuration, with Sikador 30 LP again, showed about 73.88% to be precise, higher displacement at failure than the pure GG specimens.
So it stretched almost 75% more before breaking.
Yeah. It means it gives you more warning. It bends more before it actually fails, which is often safer in structures.
That makes sense. More forgiving. So it seems like the hybrids are hitting a good balance, but what about the number of layers? They found something interesting there too, right?
They did. A key recommendation was actually that 2-layer hybrids, like GS, might often be better than 3-layer ones, like GSG or SGS.
Really? More isn't always better?
Apparently not, for ductility anyway. Adding that 3rd layer could sometimes make the whole system a bit more brittle again. It reduced the overall ductility.
Huh. So it's about optimization, finding that right balance, not just piling on material.
Exactly. That 2-layer hybrid seemed to hit a sweet spot for balancing strength and that crucial deformability.
Okay, now let's talk about something you mentioned earlier, the glue, the epoxy adhesive. How much did that matter?
Oh, it mattered a lot. The choice between Sikador 30 LP and Sikador 330 had a really significant impact. It wasn't just a minor detail.
And it seems like one generally performed better, Sikador 30 LP, especially with the hybrids and the steel mesh.
That's right. Generally speaking, Sikador 30 LP resulted in higher ultimate load capacity and also higher displacement, more ductility.
Okay.
Particularly for any configuration that included the SSWM, for instance, that GS specimen. With Sikador 30 LP, it carried about 8.7%, almost 9%.
Yeah.
More load than the exact same GS wrap using Sikador 330.
9% just from changing the glue. Why? What's the difference between them?
It comes down to material properties, revealed by looking closely at the failed surfaces, what they call fractographic analysis.
Like forensic science for materials.
Kind of, yeah. Sikador 30 LP has a lower viscosity. It's runnier.
Okay.
Which means it could penetrate deeper into the stainless steel wire mesh, creating a stronger mechanical interlock, a better bond.
Ah, so it really got in there.
Exactly. Sikador 330, on the other hand, seemed to bond better with just GFRP. But when the SSWM was involved, the bond wasn't as strong. It struggled to wet the steel mesh as effectively.
So you could actually see this difference in how the samples broke.
You could. With Sikador 30 LP, you tended to see these zigzag crack patterns. That indicates more yielding, more deformation before the final failure, more energy absorbed.
The ductile behavior.
Right. Whereas with Cicator 330, especially when SSWM was present, the failure surfaces were smoother. And they saw more instances of, like, early peeling or delamination between layers.
A cleaner break, which sounds less good here.
Less warning, less energy absorption. It suggests the bond gave way more easily.
Okay, so the adhesive choice is clearly critical, especially for these hybrid systems.
Absolutely fundamental.
Now, beyond just pulling the wraps themselves apart, you mentioned bond tests. How well did they stick to the actual concrete?
And this is arguably the most critical part for real-world application. Because if the wrap doesn't stick to the structure it's supposed to strengthen,
then the strength of the wrap itself doesn't matter much.
Precisely. So those dumbbell specimen tests were key, and they confirmed what we saw in the tensile tests, really.
How so?
The hybrid wraps, GS and SG, generally showed higher load carrying capacity and better bond strength compared to pure GFRP or pure SSWM wraps.
And again, the adhesive mattered.
Hugely, especially for the hybrids. Take the GS wrap again. Well, bonded with Cicator 30 LP, its ultimate load in the bond test was a staggering 97.43% higher than the same wrap bonded with Cicator 330.
Wow, nearly double the bond strength just by using the lower viscosity epoxy.
Almost double. It really highlights how crucial that epoxy mesh interaction is for bonding to the concrete substrate.
Okay, but here's something fascinating. This capacity utilization ratio. Can you explain that? It sounds important.
It's incredibly insightful. It basically asks, okay, we know how strong the material could be based on tensile tests, but in a real bond situation, how much of that inherent strength are we actually using before something else fails, like the bond itself or the concrete?
Right. What's the real-world efficiency?
Exactly. And for the pure GFRP wraps, the utilization was surprisingly low, only about 40%.
Only 40%? Why so low?
Because failure wasn't usually the GFRP breaking. It was either the concrete underneath crushing or, more often, the GFRP debonding from the concrete surface. It peeled off before the fibers could take their full load.
So a lot of wasted potential strength.
A significant amount. Now, compare that to the pure SSWM wraps. Their utilization was much higher, over 83% with Cicator 330 and nearly 90% with Cicator 30 LP.
So the steel mesh sticks much better.
It seems to create a much more effective bond, allowing it to use more of its inherent capacity.
Okay, and the hybrids, where did they land?
This is the really compelling part. The hybrid specimens, particularly that GS configuration with the Cicator 30 LP adhesive, achieved almost 90% capacity utilization.
Wow, so almost as good as the pure SSWM bond, but with the added strength of GFRP.
Exactly. It shows superior bonding efficiency and effective load transfer between the concrete, the mesh, the GFRP, and the epoxy. It means that hybrid system, with the right glue, gets much, much closer to actually delivering its full theoretical strength in practice.
That seems like a massive win, getting the strength and making sure it actually works when attached to the structure.
It's a critical finding.
And did the way these bond samples failed also tell a story?
Yes. The failure modes were revealing. Sometimes you saw the SSWM itself tearing.
Which is good, right? It means the bond held.
Ideally, yes. It means the material reached its limit. But with GFRP involved, especially if the bond wasn't optimal, you'd see that debonding again, or failure within the concrete layer just beneath the bond line.
So the failure mode tells you where the weak link is in the system.
Precisely. And the hybrids with Cicator 30 LP tended to show more desirable failure modes like mesh tearing, suggesting the whole system was working together more effectively.
Okay, so let's try to wrap this all up then. What are the big takeaways from this deep dive?
Well, I think the first major point is that these hybrid GFRP SSWM wraps really do offer a compelling balance. You get good strength, but also much better ductility compared to GFRP alone.
Right, strength and flexibility.
Second, the adhesive choice is absolutely paramount. Cicator 30 LP, that lower viscosity one, generally worked much better for the hybrids and anything with the steel mesh.
Well, Cicator 330 might be okay for just pure GFRP.
Seems that way, yes. Third, that capacity utilization point is crucial. Pure GFRP often doesn't deliver its full strength because of debonding.
But the hybrids, especially with the right epoxy, get much closer to their potential.
Almost 90% utilization, which is excellent. And finally, that counterintuitive point about layers. Two-layer hybrids often perform better overall, balancing strength and ductility compared to three layers.
More isn't always more.
Sometimes optimization is key.
So what does this mean looking forward for actual civil engineering projects?
I think the implications are pretty significant. This research points towards potentially more durable, definitely more cost-effective, and possibly more fire-resistant ways to strengthen structures.
New tools in the toolbox for engineers.
Exactly. By smartly combining materials like this, we can potentially build and maintain infrastructure that's more resilient to aging, environmental factors, maybe even extreme events.
It certainly sounds like a very promising direction. Okay, one final thought then for you listening to chew on. This study, as thorough as it was, focused mainly on static load conditions, just pulling or bending things slowly in the lab.
Right, controlled conditions.
But real structures face dynamic loads, right? Earthquakes, traffic vibrations, and what about long-term exposure? Moisture, freeze-thaw cycles, corrosion over decades, or a truly complex, large-scale fire.
All very important real-world considerations.
So the question for you is, how might these hybrid wraps perform under those much more complex real-world conditions? If you were designing the next phase of research, what would you investigate to really unlock the full potential of these materials for our future infrastructure?